How's it going, ladies and gentlemen? Mr. Donahue here once again. This time we're going to take a look at half-life stuff. So our objectives will include describe what is meant by half-life and solve half-life problems, which can be anything like how much time has gone by, how much would you be left with, how much did you start with, and determine the length of a half-life. All right, so what is half-life? Half-life is simply the amount of time it takes for half of a radioactive sample to decay. So let's time one. All right, let's take a look at this green sample. It decomposes into red, and we're going to time how long it takes for half of them to turn red. We're going to start counting right now. All right, let's see. There they go. Some of them decaying, turning into red. How much time does it take for half of them to do it? All right, it's almost done. How long did that take? That took about 8 seconds. All right, so it took about 8 seconds for the first half-life. Let's take a look at how long it takes for another half-life to occur. So green's still going to turn to red. We have half as much green left. So let's see how long it takes for half of the remaining green to turn to red. Ready, set, go. All right, there goes one, and another one, and another one. Really exciting stuff. How much time will this up? It looks like this one also took 8 seconds. So the moral of the story is half-life doesn't depend on how much stuff there is. If you start with 100 grams and you want to see how long it takes for 50 grams of it to be left, it takes one half-life. If you have 50 grams left and you want to see how long it takes for it to decay into 25 grams, it takes another half-life. If you had 900 grams of it, how long will it take for 450 grams of it to be left? One half-life. It doesn't matter. So for a particular isotope, the half-life will always be the same regardless of the amount of stuff that's there that you started with, the temperature or the pressure that it's under. It's constant for that isotope. So our carbon-14, if I had 100 grams of it, how long will it take for 50 grams of it to be left? 5,715 years. All right, well, what about the next half-life? I only have 50 grams now. How long will it take for me to decay into 25 grams? It still takes the same amount of time. So what? Well, knowing this, we can use this to determine the age of radioactive samples. We can use carbon-14, for example, to radioactively date organic samples. Say you're an archaeologist, you find some artifacts when you're doing a dig, and you want to figure out, well, how old is this sample? How long ago was this bowl made? For younger fossilized remains, you can also use radioactive dating with carbon-14. Uranium isotopes with longer half-lives you can use to date how long or how old rocks are. So let's see examples of how we'll need to use some math to solve these problems. Well, first, let's talk about the math. All right, things that you need to know. The amount of time that's gone by is going to be equivalent to the number of half-lives that have gone by times the length of the half-life. This probably not mind-blowing, but it's worth stating. So if you want to know how much time has gone by, you got to look at how many half-lives there's been and times it by how long each one of those half-lives is. So how do we figure out the number of half-lives? Well, sometimes they make that the tricky part. So you got to take a look at how many times you need to cut in half the amount you started with to get the amount you have. Or sometimes you got to go backwards. Or you can think of it the other way. How many times do you need to double the amount that you have until you have the amount that you started with? And every problem is going to be built upon this. How old is it? How much is left? How much was there at the start? Or what is the half-life will be answered based on these concepts. So here's an example. Fossilized remains of a plant were found. I don't know where this 16 came from, but you can ignore that. Were found at a construction site, and the fossilized remains contain 1/16 the amount of carbon-14 that is present in a living plant. Determine the approximate age of these fossilized remains. So you look up on your reference table, I found carbon-14. This is how long one half-life is. This we don't really need to know to answer the question. So I have 1/16 the amount. So let's figure out, if I started with one whole amount, one half-life goes by, I now have 1/2 the amount. If I cut a half in half after another half-life, I'm going to have 1/4. Another half-life goes by, and I have 1/8. Another half-life goes by, half of 1/8 is 1/16. So how many half-lives have gone by? Well, here's one half-life, another one, another one, and another one. So that tells me that I have had 4 half-lives. All right, well, how long is each half-life? 5,715 years. So I do 5,715 years times by 4. And I'm going to do that right now. 5,715 times 4 equals 22,860 years. So that is the age of those remains. found the plant remains. They're 22,860 years old. Cool. All right, what is the mass of an original 5.6 gram sample of iron 53 that remains unchanged after 25.53 minutes? So the first question is, well, how many half-lives is this 25.53 minutes? So I'm going to have to look up, I find iron 53 on my reference table. I see that 8.51 minutes is how long each half-life is. So if I want to know how many half-lives have gone by, I take that 25.53 minutes, I divide it by the 8.51 minutes per half-life, and I end up with, I want to say 3, but I'm going to check. And sure enough, yeah, you get exactly 3 half-lives. So now, what do I do with that? Well, I started with an original sample of 5.6 grams, and I want to know how much is left. So if I started with 5.6 grams, well, 1 half-life later, it's going to be 2.80 grams. So that's 1 half-life. Let me count a second half-life. I'm going to end up with 1.40 grams. And let me go my third and final half-life. I'm going to end up with 0.70 grams. So that's how much is going to be left unchanged after that amount of time. All right, different kind of problem. If 12.5 grams of the original sample of cesium-137 remained after 90.6 years, what is the mass of the original sample? So again, I'm going to start off with the question, well, how many half-lives is that? Well, I got 90.6 years, and I look up cesium-137 has a half-life of 30.2. So I go, all right, 90.6 years divided by 30.2 years per half-life, and I'm going to end up with, again, coincidentally, 3 half-lives. So I'm trying to figure out the original sample. So they tell me I have 12.5 grams. So I'm going to write it over here, and I'm going to go backwards in time. So going backwards in time, 1 half-life, I had twice that amount. I had 25 grams. Twice 12.5 is 25. Going back a second half-life, I would have had 50 grams. Going back a third half-life, I would have had 100 grams. So that tells me that my original sample was 100 grams. Different kind of problem. After 32 days, 5 milligrams of an 80 milligram sample of a radioactive isotope remains unchanged. What is the half-life of this element? All right, so this is going to take a slightly different approach because we're trying to figure out what the half-life is. So they tell me I started at 80 and I ended up at 5. So the question is, well, how many half-lives is that? So let's take a look. If I want to go this way, 80, 1 half-life brings me to 40. Second half-life brings me to 20. Third half-life brings me to 10. And my fourth half-life brings me to 5. So I know that I've had 4 half-lives gone by. They also tell me that it's been 32 days. So if I do 32 days divided by it being 4 half-lives, that's going to give me 8 days for each half-life. And that is going to be my final answer. 8 days. All right, summarize. Can you describe what is meant by half-life? Can you solve half-life problems? For example, how much time has gone by? How much would you be left with? How much did you start with? Or determine the half-life? Hopefully you can. If not, rewatch the video. And if that doesn't help, I'll see you in class. K. Bye.